So this lecture will cover topic 11, which is usually week 11 if you're on a 16-week schedule. And we're going to talk about independent samples t-test. So at this point, you should have finished your second midterm. We've covered all the way up through one sample t-test. This is a two sample test. So I'd like to suggest that you watch my applied hypothesis testing mini lecture now before you finish watching this, but that's up to you. Do watch it at some point. It will help really bring home how this works in real life. All right, so let's talk about our independent samples t-test. In my current textbook, it's chapter 9 through part 9.3. This chapter covers both paired and independent samples tests, but I split them up into separate weeks or units topics, right? So there are three different t-tests we're going to talk about. We've talked about the one sample t-test, right? And that's just like a c-test, except for when we don't know the population parameter. Then we have our independent samples t-test. It's for comparing means between two separate groups that have different people. And then next unit, we'll talk about the paired samples test, which compares two groups of the same people, or at least a few of the same people. For example, pre-post designs, or if I compared your grades on midterm 1 with your grades on midterm 2 to see if you're improving, right? And as I said last week or last unit, each has a different formula and different considerations, right? So now we're going to talk about the independent samples test. So let's start with differences between one and two samples tests. So we did the one sample test last time. And the one sample test, our null hypothesis is about a mean the population. So we're comparing a sample mean to the population. For example, do middle school children in Kern County read at 7th grade level, right? In other words, for our null hypothesis, we might say that Kern County middle school population mean is 7 or whatever the relevant number is for 7th grade, right? Now for an independent samples t-test, we're really addressing the difference between two groups in the population. So for example, do middle school children in Victorville differ from middle school children in Bakersfield in reading level? Our null would be that Victorville middle school students are no different from Bakersfield middle school students in reading level. So just like our one sample t-test, and a basic assumption of the independent samples test is that the dependent variable is made of scores measured on an interval or ratio level, right? So scale and SPSS, continuous scores. We cannot use nominal or ordinal variables as our outcome variable, right? Another assumption is that the populations of raw scores form normal distributions. Our sample doesn't matter if it's skewed, but the populations are assumed to form normal distributions. And here's a new one for you. So we also assume homogeneity of variance. This means that the variance, in other words, the variability or dispersion measured with the variance of the two populations are similar, okay? They are pretty much equal, right? And for sample sizes, they can be different, but they should not be massively unequal. For example, you do not want one sample to be 10 times as big as the other sample. Okay, so our statistical hypotheses. Now here, I want you guys to add these to your little cheat sheet of all your statistical hypotheses so everything's organized, right? So for a two-tailed test, the null hypothesis is simply that there's no difference between the means. This translates to that if you subtract mean 2 from mean 1, it's going to be 0, right? The alternative hypothesis, which is your research hypothesis, right, is that the means are different. This translates into if you subtract mean 2 from mean 1, it's not going to equal 0, right? So what if you're making a directional test or one-tailed test? So if mean 1 is expected to be larger than mean 2, then our null would, well, let's start with the alternative here, okay? Mean 1 minus mean 2 is greater than 0. Our null is always the opposite with an equal sign. So mean 1 minus mean 2 is less than or equal to 0, right? If alternatively you expect mean 2 to be larger than mean 1, then it's just the opposite. Mean 1 minus mean 2 is going to be less than 0. And for the null, it's going to be the opposite. Mean 1 minus mean 2 is greater or equal to 0. Now, in practical terms, you can set this up however you want. You can I like to think of the mean that I expect to be larger as mean 1, and the one I expect to be smaller as mean 2 if I do a one-tailed test. So I pretty much always conceptualize it like this, but it's not important as long as you have it clear. Okay. So here's the idea behind the null hypothesis for a non-directional test. So you're comparing two groups, and the idea is that both samples come from the same population of scores. They do not come from different populations, right? And the alternative implies that each condition comes from a different population of scores. All right, so go back to, I'll talk you through an example later because it's the same example I use all along. All right. So the sampling distribution that we're using is the sampling distribution of the differences between the means. And this is just a distribution of all possible differences between two means when both samples are drawn from one population. In other words, the null hypothesis, that is the same population. All right. So if you think about this, we look at our, right? The null hypothesis says that the difference between the means is 0, right? Is 0, all right? So this would be that most differences between the mean, if the null is 2, are going to lie right here, right? But what if there's a big difference and mean 1 is greater than mean 2 in our example, right? This would be a big difference here. This would be our region of rejection, right here. And our idea would have to be so unlikely, given this null, right, that the differences between the means are going to be fairly close to 0. Is it so unlikely that we can reject the null hypothesis, right? So some differences between 1 and 2 sample tests. So in the null hypothesis for our one sample test, as we've been doing, we just have that the mean is equal to some hypothesized value, okay? With a 2 sample test, the independent samples, the null is that there is no difference between the means, right? Mu1 from minus mu2 is 0. Then we have how we calculate t. So we've already gone through one sample test, just the sample mean minus the hypothesized population mean divided by the standard error of the mean, right? For our 2 sample tests, we have the sample mean 1 minus sample mean 2 minus the null hypothesis means, right? So this is going to be 0 because the null is that this equals 0. So this is all we're going to have here, right? Then we have the standard error of the mean. And we already done this, right? This is just the standard deviation of the sample divided by the square root of n, which we use to estimate this because we don't know the population parameters. For our 2 sample tests, this is the standard error of the differences between the means, right? This is assumed to be 0, right, in the null. So this comes to 0. So it's just the square root of the variance of sample 1 plus the variance of sample 2. Now, important. Now, I'm not going to ask you to do any calculations of these, but you do need to know the degrees of freedom for an independent sample t-test, and it's just the sample size 1 plus sample size 2 minus 2. All right, all the people minus 2. Finally, we have our confidence intervals. So on the left, we have the confidence interval for a 1 sample test. It's just the mean plus or minus your critical value of t multiplied by the standard error of the mean. And for a 2-tailed test, it's the difference between the two means plus or minus the critical value of t multiplied by the standard error of the differences between the means. All right. So what does independent mean? This just refers to the participants in our groups, how the groups are constructed. For an independent samples test, the people in each group must be different, right? The presumption is that they've been randomly assigned if it's an experiment, but mainly they cannot be the same. So for example, if you have 100 people come into the clinic, you can randomly assign 50 to receive treatment and 50 to a waiting list, a wait list control group, right? They're different people. If we compare 7th grade and 10th grade students on math achievement, all in the same year, we're not taking them in 7th grade and repeating 3 years later. No, these are separate people, right? Gender differences, we use independent samples t-test for gender differences. So if we have the same people in both groups, then it is not an independent test, and it would be inappropriate to use the independent sample t-test, right? We would use pair t-tests or related samples, and we'll talk about that next topic. Okay, so let's walk through an example from the research. So this is participants came to lab for a taste preferences study. This were what they were told, right? And this is a cover, right? So they were seated in the waiting room with 2 other participants who were really Confederates. The real participant was randomly assigned to either be ostracized or included. And the way this worked is that one of the Confederates took a toy from a children's play, a basket, it said children's play study, and started tossing the ball. In the ostracized condition, the participants received 3 tosses, but then found themselves shut out. Then they were totally ignored, and the 2 Confederates just threw the ball in between themselves, totally ostracized, kind of like that piggy in the middle or whatever. In the included condition, it was just normal. They had about 1/3 of the tosses for the 4-minute period, right? And this is the citation of the study. After that, okay, the participants think that's just, they're waiting in the room and it's just coincidence, right? They're moved to a separate room and they're told, okay, now we're going to do the experiment. We're going to do this taste testing study thing. And they would take a slip from a hat that they were told, okay, this will tell you what category you're going to package the food for, but everybody got the same slip and it said category 5, hot and spicy. And they got hot sauce, cups, lids, and a spoon. And then they allocated hot sauce according to the instructions. And what it said is that the taster, someone was going to taste this, and it was clear that was not the people that had been tossing the ball, right? Had to consume the entire sample of hot sauce, and they should read the preferences from the sheet in the sealed envelope to ascertain whether or not that person was allergic to the sample, right? So everybody read that the taster had rated hot and spicy foods at 3 on a 21-point scale, which is that they really don't like it, right? Then they tasted it to verify it was spicy. And then they were told they filled up the cups, right? And after filling the cups, the researchers took the sauce into a separate room and weighed it. So aggression was operationalized as the amount of hot sauce allocated to a stranger when they knew that the stranger did not like hot and spicy food, and that he or she would have to consume all of the sample, and that it was really hot. So let's think about this. The null hypothesis is that it doesn't matter, right? That it doesn't matter if you're ostracized, you're not going to be any more aggressive. So mean hot sauce allocated by group 1 minus group 2 would be 0. No difference in hot sauce. Here we have the results, right? We have the mean from the ostracized condition, 28 grams, I believe it was, compared to 4.9. That looks like a pretty big difference, right? So let's look at the output from, this is old SPS output, but I love this example, so we're still going to use it, right? So we have the standard deviation for each group. Let's have a look at this, okay? Right? Big differences here, right? Standard deviation for ostracized is huge. Standard deviation for included is small. Now, right now, we know that something is going on because included, pretty much everybody was nice, didn't allocate much sauce, right? Grams of sauce. In the ostracized condition, some people allocated a lot, really a lot, and some not very many, okay? Here we see the standard error of the mean on the right for each. This is the standard error for each group, okay? We're not going to worry about unequal variances, but you would use this if you're going to calculate to compensate for unequal variance. Okay, so here's our output. And let me get a pen. So as before, we have degrees of freedom. It goes in parentheses after the t-value, okay? Then we have our t right here under t. Now, currently, as you guys know, let me erase all these drawings. Okay. As you know, now SPSS gives you the significance for a one-sided and a two-sided test. This is old days SPSS where they didn't have less than 0.001 and they had just two-tailed, right? You had to actually divide that to figure out what it would be for one-tailed. We still have to do math with SPSS, but it's not quite the same, right? So we see it's less than 0.001, okay? We know right there that we will reject the null hypothesis because it's less than our alpha level 0.05, right? Here we have the standard error of the differences between the means. That's that equation that we saw, this value in the equation we saw before, right? We also have a 95% confidence interval for the differences between the means. And this is just an estimate of what the value, the difference between the means of the two groups, people are ostracized and people are included, could be in the, if we have the population values to calculate it with. All right, so here we have that confidence interval. We write it 95% CI confidence interval, a bracket 11.31 comma, and the upper limit and another bracket. And this just means that the difference in the population could be anywhere between 11 and 35 milliliters, not milliliters of hot sauce. So how much is this really? What does this mean? Okay. So look at these. That's like almost 4 liters of hot sauce, you know, less, and then a little tiny hot sauce that would last me about 1 taco, right? But I like hot sauce, right? But let's look at it per group. So in the included condition, 4.9 milliliters, okay? Just a couple little guys, 1.5 little guys, right? Ostracized, if we use the same size, look at how much that is. But this doesn't really mean anything to us. As researchers, we're not too interested in the fact they assign more hot sauce. We want to be able to say that, hey, ostracism makes people more aggressive, right? And, you know, in real life, nobody's going to be assigning hot sauce, but they might be doing worse things. So to make this more interpretable, we calculate an effect size, right? And usually Cohen's d, at least that's what we're going to cover in this class. Our t-test, which we base our statistical decision on, is basically just the question of, do the groups differ? Is there an effect? Is there evidence that in the population, there's a difference between these groups, right? The denominator of your t is a function of the standard deviation and your sample size. Okay, this means that if you have a big enough sample, you're always going to have a big enough t-value to reject the null hypothesis. Doesn't matter how small the effect is, right? Cohen's d, or d, right, is really answering the question of how much do the groups differ. So your p-value or t-test is, is there a difference? Your Cohen's d is, how big is the difference, right? That's the effect size. Here, the denominator is just a function of the standard deviation, the average of the two, right? And so it's independent from sample size. All right, here's the d equals to the difference between the means divided by the pooled standard deviation, okay? So let's think about this. Why not just mean differences? Again, this doesn't tell us much. Mean difference is about 23 milliliters. What does this mean? What does this mean in terms of regression? Not much, right? But D, which is kind of a standardized measure. So you can think of this as 1.125 standard deviation. So if we say that ostracized people exhibit 1.25 more aggression than included people do, that is more meaningful, okay? All right, let's walk you through one more example. So say we expect that men and women will have differences in empathy. So we can predict as researchers, our research hypothesis is that men and women will self-report different levels of empathy, right? Here are our statistical hypotheses. Because it says we'll self-report different levels, this means it's a non-directional test or two-tailed test. Our null is just that the difference between the means is not 0. So mu1 minus mu2 is n equal to 0. And that was our alternative hypothesis, sorry. And our null hypothesis is that there is no difference, that mu1 minus mu2 is 0. So we run our hypothesis, we run our analyses, right? This is modern SPSS output. So I want to call your attention to these different things. So we have First, we have a table with the statistics. We have N per group. We see there's more females than males, but there's not 10 times as many, right? We have the mean for both group, okay? We can see right here that, yes, it looks like females self-reported greater empathy. Standard deviation, the standard error, the mean for each group separately, okay? Then we have, this is the part of the output you're going to be looking at. Remember, we're assuming equal variances, so we're just looking at the top row, right? We see our t-value is 3.67 degrees of freedom, 253. Here we're looking at a two-sided p-value. It's less than 0.001. Okay, we also have our mean difference and a 95% confidence interval around the differences between the means. That was a bit sloppy, right? So remember, we're just looking at this top end, right? Okay. So how do we report this? Here's the full output from SPSS. Here we have the means and standard deviations of both groups, okay? Remember, we are going to do equal variances assumed for this class. And here we have our t degrees of freedom and p-value, whether one-sided or two-sided. And this is our Cohen's d, or point estimate. We also have confidence interval for Cohen's d there. And here is our statistical jargon way to talk about it. Women, and we say the mean and standard deviation, reported greater empathic concern than did men, mean standard deviation, than our T, P, and D. In plain English, women had greater empathy than men. Women show greater empathy than men do, all right? So a few more things. First, critical values are determined on degrees of freedom and alpha level, just like with our one sample t-test. If you were going to be using a t-table, you would do it the exact same way that we talked about last unit, okay? So decide if it's one-tailed, two-tailed, alpha level, and we figure out our degrees of freedom, which is N1 plus N2 minus 1. To construct confidence interval, which we are not going to do for this class, okay? We just use the difference between the means because it's a confidence interval, 95% confidence, for example. If our alpha level is 0.05, that corresponds to a 95% confidence interval, plus or minus that critical value of t, okay, times the standard error of the differences between the means. All right, which translates into this. Okay, brief review of power. Remember, to increase power, we can have a bigger effect size, okay? Maximize the size of the difference between the means. You can't, in the population, the difference is the difference, right? Either ostracism makes people more aggressive or not, and that effect is going to be more or less the same, but you can do the best to measure it properly and so forth. Bigger sample size, okay? More people, you always have more power. And then one of the key things is less within group variability, the standard deviation of each group. So our example, we saw we had a huge standard deviation for the ostracized condition, and that actually cuts down on power, okay, because of the math behind that. So if you can minimize the variability of the scores within each condition, you're going to have greater power. The best way to do that is to use the same participants in each group. So in our example, we'd have the same people. One day they'd come and they'd be in the ostracized condition, and then maybe a couple weeks later they'll do a different experiment with a different facade, a different story, and then they'd be in the included condition. Then we compare how aggressive they were, right? And that's what we'll cover next topic. All right, so one more thing. So for this unit, I have assigned a game for you to do that will help you understand independent samples t-test, standard deviation, power, and so forth, okay? So you can go to this game portal at the K20 Center where I worked years ago, click on sign up and enter this invitation code into the invitation field, right? Completing the game potions will earn you 10 points extra credit. I also have deadly distribution. It would be great for chapter 3, and in the future I might be assigning this in chapter 3, in which case if you're watching this, you might have already seen this, but you can do it as well. But at this point, do potions first to get extra credit. Then if you want to do deadly distribution and complete it, I'll give you extra credit for that one as well. All right, that's it.